Have you ever told a long story only to realize they forgot how it started? Early AI had a similar problem. Older systems were built to process text exactly like we do, one word at a time, strictly from left to right. Each word hands its meaning off to the next in the line. The machine tries carrying the memory of the first word down the line, but as sentences grow, that memory fades. Take the phrase, "The law will never be perfect, but its application should be just." Reaching its, the connection to law is lost. Reading in a strict line creates a bottleneck. Because the machine has to wait for every word to finish before moving to the next, it prioritizes the order of the words over the actual meaning of the sentence. This diagram illustrates a different approach proposed by researchers in 2017. They published a paper called "Attention is All You Need" and introduced this architecture called the transformer. The core idea is to abandon the relay race entirely. Instead of reading one word after another, the transformer takes in the entire sentence at once. Because it doesn't wait for word 3 to finish before looking at word 4, it can analyze different sections simultaneously. By setting aside the strict left-to-right reading rules, researchers bypassed the speed limits of older models. They could now train massive systems in a fraction of the time. To make this all-at-once processing work, the transformer uses a mechanism called self-attention. Imagine a detective's evidence board. The AI pins every word up at once, drawing lines between mathematically related words to map the phrase. It doesn't carry a fading memory from law to its. It instantly draws a direct line between them. Physical distance within a text stops being a problem. By evaluating the relationships between all words at the same time, the computer maintains a grasp of the context regardless of how long the sentence is. To sharpen this analysis, the system uses the feature shown here in purple, called multi-head attention. Think of it like having 8 separate detectives investigating that same evidence board at once, each focused on a different layer of the sentence's meaning. One detective might track how the verbs relate to each other, while another focuses on the subjects, and a third looks at the emotional tone. Each detective maps out these distinct patterns of relationships simultaneously. Stacking these distinct mathematical perspectives on top of each other gives the machine a multi-layered understanding of language that earlier systems couldn't achieve. When the researchers tested this approach on translation tasks between English, German, and French, it set new records for accuracy. But what stood out was the incredible efficiency. The architecture hit these high scores after only 3.5 days of training on standard hardware, a fraction of the time required by previous systems. There is a trade-off for this speed. Because the computer draws a connection between every word and every other word, the mathematical work piles up much faster than the length of the text itself. Processing a short document happens very quickly, but if you try to feed the model an entire 500-page book all at once, the sheer number of crossing lines creates a massive demand for memory. Even with that heavy math requirement, the gains in translation quality and training speed effectively retired the era of one-word-at-a-time models. Today, this 2017 architecture serves as the strong foundation for almost every major conversational tool and translator we use. Researchers are now applying this exact blueprint to other types of data, proving that this attention mechanism works just as well on audio recordings or maps as it does on text. This shift replaces the slow, one-word-at-a-time approach with a system that sees the global structure of the data, allowing the machine to work on everything in parallel. Establishing these direct links across an entire dataset at once is what allows machines to navigate the intricate ways we use language.